Quantum tunneling has always been something that is well known, but it's been well known for small numbers of particles, right? With even with nucleons and alpha decay, that's like 4 protons, right? Four sort of, it's a pretty small mass,
Yes.
right? What this year's Nobel Prize winners did was experimentally confirm quantum tunneling and quantum behavior for like on the order of a billion individual particles, all acting together and quantum tunneling together.
Interesting.
Okay,
Okay,
so
yeah,
it's
that's
several orders of magnitude
magnitude.
above that sort of undergraduate level
Understand.
like problem sets that we used to do.
Right.
It's very cool, I think. So if we have like a classical particle
Yes.
and you've got like, let's say a wall, like a brick wall, and I like throw stuff at it, it's gonna bounce right back. In no world is a ball that's the size of my hand ever gonna go through. Right? In the quantum world, that's no longer the case, right? You can have a barrier and then have a single particle go through. And this is something that you can solve in undergraduate physics. Just using the Schrodinger equation, you've got some particle with initial energy going from left to right, okay? Notice that on the right-hand side, the wave function is highly diminished.
Yes.
So what that means is that the probability of finding the particle on that side is way smaller than finding the particle on the left side, which makes sense, right?
Yes.
I'm going from the left side, so the probability of tunneling is low.
Yes.
But crucially, notice that the waviness of the wave function on the right is the same as on the left, meaning the wavelength hasn't changed.
Yes.
And what that means is the energy hasn't gone down.
Right.
It's almost as if the particle just teleported through
without
this
actually.
energy barrier.
Yes.
That's very not classical.
Right.
Yes. That is very much like not a classical thing.
Yes.
Right? In a classical thing, that's the magic of quantum mechanics there.
Right.
Okay?
Right.
So historically, it's actually been seen in all sorts of different phenomenon. Like, for example, with radioactive decay, this is the idea where nuclei, like large nuclei, like the uranium atom, can decay when they spit out an alpha particle, right? And it happens with a certain probability. That can actually be modeled using this quantum tunneling landscape. What you can imagine is you've got the nucleus of the atom, and the nucleus of the atom has a bunch of particles that are kind of moving around, right? The protons or the neutrons. And if the proton or neutron tunnels itself outside, and so